Okay, so let us continue. We were talking about how to calculate the efficiency. So we calculated already Y from the energy balance on the open feed water heater. Next step will be to determine Qn and Qout for the different parts in order to calculate the efficiency. So if you go back to our figure, okay, we know that the input will be through the boiler. So at the boiler level, we have Q input, and the mass flow rate through the boiler is the total mass flow rate. You have the total mass flow rate will go through the boiler. So if we are reasoning in kilogram per second, so you have 1 kilogram per second that is going through the boiler, and we can calculate then Q dot N as 1 times m dot times delta H. So it's 1 times H5 minus H4. Since we have one boiler only, so this is the only location where we have input of heat. Okay. Now, concerning Q out is at the condenser level. So we can calculate Q dot out. Here we should pay attention that only if you want 1 minus y, the fraction 1 minus y, okay, will go through this part. Okay, so we have here, this is why we have some reduction. So here we have reduction of the total work of the turbine, because not the whole mass flow rate will go from 5 to 7. Okay, so through this system, we have that the flow rate that will go through the condenser is 1 minus y. So we'll calculate it as 1 minus y. Q dot out is 1 minus y times H7 minus H1. Within the open feed water heater, you cannot consider it's a closed system. Okay, it's not you have exchange just between the fluids, so it's internal exchanges. You will not consider them as Q dot in or out. Okay, so because as we did the analysis, you just have heat transfer from between the fluids. Okay, so you have the mass flow rate y, and mass flow rate 1 minus y will exchange heat to come up with an intermediate point. You have the flow rate that is going through this loop here, so that is undergoing this stage. Okay, and the one that is coming from the pump, this one will lose heat, this one will gain heat, and the last heat is equal to the gained one by the 2 parts of your divided flow rate. So this is why this is an internal exchange of heat. It's not an exchange with the outer environment. This is why you don't include it in the efficiency calculation. In the efficiency calculation, you just take into account Q dot in and Q dot out, and you just do 1 minus Q dot out over Q dot n. And we can see here, we can see the efficiency, because Qn will be largely, if you want, when we do this, okay, you have that the heat input to the boiler will not be will be reduced, because we have the area. If we do the analysis of the area here, okay, will avoid a big part here will be avoided, because we are using the system. So what now, once we write the equation for efficiency, Okay, we can consider that Qn is H5 minus H4, Q out is 1 minus Y H7 minus H1, and then we are ready to calculate the efficiency. The efficiency in overall is, as we know, okay, is the work output W net over Qn. So it's of interest to decrease the Qn in order to increase the efficiency. And we were able to do this because by using our system, we increased the temperature entering the boiler. And then by increasing this temperature, we need a lower amount of heat, okay, to reach the state at the exit of the boiler, which is expected to increase the efficiency. From the other side, it's true that W net is reduced compared to the conventional Rankine. This is why to see the improvement, you should compare this problem with another one operating at the same extreme conditions. And if I take same P minimum, P maximum, it's true that I will lose some part of W net because the reason of this is that I am not expanding fully the fluid in the turbine from big pressure to the low pressure. But on the other hand, I am reducing much more Qn. This is why in overall I will gain. So if you do a small comparison, if you repeat the same problem for a conventional Rankine working between P minimum and P max, you will get the following. You will get that the net work output is decreased by 171 kilojoule per kilogram. However, on the other hand, the heat input is decreased by 607 kilojoule per kilogram. So in overall, Qn will decrease much more than W net. And in overall, if you calculate the efficiency, it will be, you will increase your efficiency from 43% for a normal Rankine cycle to 46.3 for the regenerative Rankine cycle. Okay, so we can see here the importance of using the feed water heater. Now, sometimes we use several, instead of one feed water heater, we can use several ones to increase the efficiency. But always remember that if you should compromise between cost and efficiency. So if you increase the efficiency by 3% with a small cost, it's fine, because if you have to put a large cost to increase the efficiency by a small percentage, then you might not go for it, because you will need to have, you should make sure that your system is economically viable. So no one will invest for an increase of 1% in efficiency if the cost is very, very high. However, if the cost is affordable, and if you will learn in this course at the final chapter how to do an economical analysis to make sure if the idea we are proposing is economically viable or not, if we get profit from it, and what is the time needed to start to get profit. This is what we call the payback period. So it's very important, if you introduce any modification to the system, to make sure that this modification will lead to benefits in the incomes, not only in the increase of efficiency, because it's true that it's increasing the efficiency, but also we have a larger cost of implementation of the feed water heater. Okay, any question on this problem? Is anything not clear? I will do another revision problem that is, if you want, including both chapters 2 and 3. So how we apply the energy balance plus the knowledge for heat transfer by conduction, convection that we learned in the first chapter. So let us consider the following one-dimensional conduction in a plain composite wall. The outer surfaces are exposed to a fluid of 25 degrees and a convection heat transfer coefficient of 1000 watt per meter square Kelvin. The middle wall B experiences uniform heat generation, Q dot B, while there is no generation in walls at A and C. The temperatures at the interfaces are T1 equals to 261 degrees and T2 equals to 211 degrees. The first question is, assuming negligible contact resistance at the interfaces, determine the volumetric heat generation Q dot B and the thermal conductivity of material B. So to start with, we have two unknowns here. We don't know the generation rate, Q dot B, and we don't know the thermal conductivity of the material at middle between A and C. Whenever you have such problems, okay, please pay attention. Whenever you have generation, you cannot just deal with thermal resistances. Because if you remember, when we learned how to draw the analogy between thermal circuits and heat circuits, we said that we should have pure, let's say we have conduction or we have convection fluxes, and we have resistances associated with them. So if you remember, for convection, for example, the resistance of convection is equal, can be written as 1 over H times A. No. Okay. However, for case of conduction, we have we can write it R conduction is equal to L over Ka. Okay. So we know how to deal with resistances and how to draw the circuit of resistances in case we don't have generation. Whenever we have generation, okay, we should do the analysis of this part alone, and then we'll see how the heat generated here will be propagated to the system. Okay, so whenever you have generation, please think about how to write an energy balance that can help you to solve your problem. So you say, I know that I have a generation rate in material B. So let me write the energy equation for this material. We have generation, okay? And this generation will be propagated through two sides, from the side of A and from the side of C. So if I just apply the energy balance equation, what can I say? If I am working in steady state conditions, then I don't have variation with time. So what is generated inside should be propagated to the outer environment, should be lost to the outer, towards the outer environment. So I can say that Q from energy balance, Q dot generation, okay, is equal to Q dot out at interface A plus Q dot out at the interface with C. So this is the key equation to solve your problem. Okay, so first you need to write the energy balance for the part where you have generation of heat. This will allow you to correlate with the heat fluxes through A and C. Once you do this, you know how to deal with the remaining part, because in chapter 2, you know that how to write if you want the analogy with an electrical circuit from interface 1 to T infinity, because you can say this. If I know T1, okay, I have first, when I go through material A, I have the resistance associated with conduction. So I can write L over Ka. And when I go through, when I have convection with the outer side, I can write here to go from T surface, if you want, we can call it T surface of A. From T surface A to T infinity, we have the convective resistance. So we have H, so we have 1 over HA. Okay, and what the heat flux that is going through this thermal circuit is Q through A. Okay, is the heat rate through through A, which will come from the generated heat. So it's this part. It's Q dot out from A if you want. Okay. So Q dot out from A is what? Is Q at A that is going through A. Okay. And can be calculated through the thermal resistance concept, because I can write that QA is equal to delta T between T1 and T infinity over sum of resistances. So I can get, if you want, Q dot out through A. You have several symbols you use. Maybe you are familiar with Q dot, or you are just calling it Q if it's the total rate in watt, and per unit area you call it Q second. It doesn't matter the names. Okay, just what matters is that you know how to treat the problem. So you can call it Q dot because it's in watts. Okay, and then you can say I can get this flow rate by using the thermal circuit analogy. So I use delta T over sum of resistances. So from side of A, what can we write then? We can write that Q dot out from the side of A can be just computed as T1 minus T infinity over sum of resistances, which is the resistance of conduction and the resistance of convection. So I have L over Ka plus 1 over Ha. So then I am done with the first part. I calculated the first part. I will do exactly the same procedure for the part that is getting out from side of C. So I can write that Q dot out from side C is equal now to T2 minus T infinity over L over Ka plus 1. Of course, when you deal with part A, you will replace by K of material A. And the convective coefficient is the same from both sides, so H will be the same. Here you will put KB, and of course here this is L, the thickness of material A, and here you have the thickness of material B. So plus 1 over H times A. You have all your inputs here. You have your temperatures, you have the lengths of parts A, B, you have the conductivities in A and C, I mean. So here it's LC. Okay, you have conductivities of parts A and C. You just replace, so you can calculate Q dot out from side of A and Q dot out from side of C, and then you will be ready to find what is Q dot generation. And once you find the Q dot generation, you can go back to your question to find what is the volumetric heat of generation, because small q dot b is big Q dot B over the volume. So Q dot B over the volume of generation. And the volume of generation is 2LB times the area. Okay. This is why there is no need to know the area, because the area will cancel out. Okay. Because Q dot conduction and Q dot convection are through this area. And also, when you express the volume of generation, it's A times 2LB. So the area will be simplified from your terms, and you can get the expression of the value of the generation per unit volume, or volumetric heat generation Q dot B. So this is how we solve for a Q dot B. Okay. Now, concerning the thermal conductivity of material B. To find it, okay, we need to know properties about temperature variation in B. In this course, will not go deep into heat transfer. So my purpose is just for you to know how to put energy balances, how to find relations between fluxes getting in and getting out. But I just want you to know that in a problem, in an exam, I can tell you, for example, that the distribution of temperature, the profile of temperature within B, because you have heat generation, is a second degree equation. So for example, I can give you the form of the second degree equation, okay? And I can tell you then to find the profile of temperature and to calculate the conductivity of B. How to calculate the conductivity of B? Any idea? Who can tell me how can I find KB? Based on what? Based on which equation I can calculate the conductivity coefficient KB?
Based on delta T over L.
Okay, look, you cannot do this in material B because you have heat generation. Okay, it's true if it was in material A or material C, because in material A or C, you just have conduction flux. Okay, it's a constant conduction flux, and then you can say that I can calculate K based on, because I have linear profile in A and C of temperature, I can do delta T over L. It's completely right, but only right in A and C, because in A and C you have a constant conduction rate. However, because in B you have heat generation, you will not have a constant conduction rate through your within your material B, and that's why what you can do is you can do the analysis on the interface. On the interface, you can say that the heat flux that will go outside of B is a heat flux by conduction. So you can, and because at the interface you have constant, the rate that is getting out from B is equal to the rate that is getting inside A. So you can say that Q conduction at the interface at level B is equal to Q conduction within material A. And of course, you can also apply this rule at the interface with C. So if you apply it or at the interface with A or at the interface with C, you can calculate the conductivity Kb. Why? Because you can write that Q conduction is minus Kb times A times dt by dx. This is the formula, okay? dt by dx in material B, of course, equals to the conductive flux in material A, which is minus Ka times area times dt by dx in material A. Now, since it's the same area, the area will cancel out. But since you have generation in B and steady state and no generation in A, okay, in A you have a linear profile of variation. So in the course material, you are just responsible to know that when you have when you don't have generation, okay, only pure conduction, you can calculate the flux dt by dx as minus, if you want, minus delta t over delta t in x direction over the length, okay? But because if you want, the temperature at 1 is larger than T1 is larger than the temperature at this level, okay? So it's T1 minus this temperature over L. But no need to do this calculation because we already know what is the flow rate, what is the heat rate Q through A, okay? So we can say that this minus Ka dt by dx at A is equal, so if we call this temperature T surface of A, okay, we can replace now, we can say minus Ka times T surface at A minus T1 over LA, and you can also, the minus, if you take it inside, you will get minus T surface at A plus T1 over LA is equal already to Q conducted at A, which is already computed from the thermal resistance system, is equal to minus KB, So let me write it again in a clear way. So you have Ka times T1 minus T surface 1 over LA, or T surface A, over LA is equal to Q dot A. Already we calculated Q dot A from the thermal resistance system, so we can calculate T surface at A now, because we know Q dot A. From this equation, we can calculate T surface at A if they asked for it. If they don't ask for it, no need to calculate it. You just say that Q dot A is equal to minus KB times dt by dx at the interface, okay? Now, how to get dt by dx at the interface? You cannot continue, you cannot solve for KB if you don't know this term, okay? That's why here they should help you. They should give you the equation of temperature profile. And I will do this, of course. And in the exam, if I give you such thing, I will tell you, because I'm not supposing that you know this. I just suppose that you know whenever you have pure conduction, the profile is linear. Okay, but if you have generation, you can demonstrate, but it's not the scope of this course, that for constant generated uniform heat generation flux, you have a parabolic profile for the temperature variation. So I will tell you in the exam, I will tell you that within material B, you can say that the temperature variation is given by the following form. So I will tell you that you can write the temperature variation as following. Temperature function of X is minus QB over 2K X squared plus C1X plus C2. So this will be provided for you, okay? You will be given this, but you should know how to proceed, how to treat, how to work with this information. So you know that material B is bounded from two sides, and you know the temperature at side 1, and you know the temperature at side 2. Okay, and we already solved for Q dot B from what? From the energy balance. So whenever you take the overall energy balance of material B, you get Q dot B. So you still have only one unknown, which is KB. To deal with it, let us first find the constant C1 and C2. We need two boundary conditions to solve for C1 and C2. So since we have here, let's say, you have here 2LB, and we can take the origin of our x-axis, let's say, if you want to take it here at the middle of the material B. So you have here at this level, so if this is the origin, at this interface, you have x is equal to plus LB. And at this interface here, you have x equals to minus LB. So you can say, to determine my constant C1 and C2, I consider that T at plus LB is equal to T2, which is given, okay? So this will give me a first relation between constant C1 and C2. And the other boundary condition is that T at minus LB is equal to T1. So now you will be able to solve for your temperature profile constant C1 and C2, okay? We still have just one unknown, which is KB. In order to find KB, we need another relation, which is the relation of that we discussed together, of the constant heat rate at the interface. So the heat rate getting out from B towards A is a conductive flux. It can be written within material B. If we write it within material B, it's equal to minus KB times dt by dx, because we are expressing the flow per unit area now, because the area was simplified. So now all I need to do, I know Q dot A. I calculated from the thermal circuit of resistances. I just need to compute dt by dx function of KB. and I should evaluate it at interface 1 if I'm working with material towards material A, and I can do the same work if you want between B and C. So if I work with the second interface, I say that Q dot B is I divide per the area, per unit area, is equal to minus KB times dt by dx, but now at x equal to plus LB. While if I do the analysis from the side of A, I do minus KB dt by dx, but for x equal to minus LB. So now, after you got your temperature profile, you say this is the equation of my temperature, and I know C1 and C2 from boundary condition, I can find what is dt by dx. So if I do the analysis, I write dt by dx, if I derive this equation with respect to x, I get dt by dx is minus 2 q dot b times x over 2kb plus C1. And now this is the general equation. C1 is already calculated. I can compute dt by dx at any location. In particular, the location that is of interest for me is dt by dx here. Okay, at x equal to minus LB. So I can find then the flow rate. Okay, I can find what is dt by dx at this level, and by using the equation, I can compute then what is kb, because when I equate the conduction flux that is getting out from here, okay, with q dot a, I can get my result. Okay, just one information, please pay attention. Here we know that the temperature will be maximum somewhere within the material, not at the middle because we don't have symmetrical condition. So you have maximum and the temperature is reduced. Okay, so when you compute at this level here, okay, when you compute dt by dx, you will get a positive or negative result. Who can tell me?
It's negative because it's losing.
Yes, you have when you consider, because dt temperature is increasing in this direction. So if this is your x-axis, if you consider your x-axis in this direction, this is a positive convention we are taking for the x-axis. Okay, you will get here dt by dx to be positive. Okay, and since this is why we say that knowing that dt by dx is positive at this side, okay, and we have that heat is larger within the wall, larger than the outer level, then you will have always your flow rate will be in the direction opposing dt by dx. So your flow rate will go outward. Okay, this is why when we compute, if you want, in general, when we say the flow rate is minus k dt by dx, we assume that the flow is in this direction, okay? But now if you put your flow rate getting out, and because you know that your flow rate is getting out, okay, then you reverse the convention. Okay, when you put your flow rate in this direction, then you don't put any more minus, you put plus k dt by dx. Okay, so just pay attention for the convention of sign. Always when you take if this is the positive x direction, okay, when you take the flux along positive x, you put minus k dt by dx. But because we reversed it here, we know that the heat flux is going in this direction, then you can take the absolute value of minus k dt by dx. Okay, and then so you just have to take the absolute value of this and say apply it at x equal to minus LB, and say that this should be equal to the conduction, the flux rate, the rate per unit area from the side of A. and then you can compute the value of Kp. Okay, so please be familiar with how to apply energy equations whenever we have generation. And for the remaining part, in any part where you don't have generation and steady state case, you can deal with thermal resistances that you learned in chapter 2. So this problem is combining concepts from chapter 2 and chapter 3. Okay, and you should be also familiar with different types of boundary conditions. So let's say if I have a wall, you know it already. If I have convection, for example, okay, how can I write at this level the boundary condition? I can write that if this wall, for example, is at x equal, let's say L, so I can say that Q conduction at x equal L is equal to Q convection. Okay, and we know how to express Q conduction at a certain point is minus K dt by dx at this position, and the convective flux is computed as H times A times delta T. Okay, so in general, we know the direction of heat transfer. So you can just take the absolute value of Q conductive, okay, equal to HA times absolute value of delta T. So you always take T max minus T minimum. And you evaluate Q conduction from the equation. In case it's a you don't have generation within your wall, then simply you can say that Q conduction is K times big temperature. So T, let's say you are having the transfer. So let me put it again here. So if you have a wall, for example, okay, and you have a certain thickness L, and you know that you have only conduction here, and this is T2 and this is T1, okay? Let's say that T1 is larger than T2. So of course, you know that heat will be propagated in this direction. So you can write that Q conduction here is equal to minus K dt by dx, let's say here at x equal L, okay? But because here it's a linear profile of variation of temperature, no need to do derivative because you know it's linear variation. You can directly put then K times T1 minus T2 over L. And then this will be equal to the rate that is lost by convection, which is H times delta T, which is T2 minus T infinity. Okay, so you can use boundary conditions always. So these equations can always be used in order to determine 1 hour unknowns. So they are called boundary conditions. So here we know, for example, that it's convection. In this problem, it was first conduction after convection. So depending on the location you are working in, you decide which relation to use. In this problem, you are forced to use the interface, okay, because you want to get K at the level conductivity of the inner material, and the inner material is not exposed to convection. It's interacting at the interfaces with materials A and C. So here you have Q conduction that is computed by K dt by dx, and to find dt by dx, you need to know the temperature profile. This is why they gave you here the temperature profile within this material. However, if you are working from the outer side, for example, here, you know that it's a linear profile, so you can directly apply that Q conduction from linear profile is K times delta T over F equals to, from the convection side, the heat will be HA delta T. So you can directly apply this. However, here at this interface, you need to know the profile of temperature to compute dt by dx. Okay. Any question on this?